session with the first part of modern physics, which is about photoelectric effect. And through that, we will understand about photon theory of light. As the name suggests, photoelectricity or photoelectric effect is about the generation of electricity by light. Okay. So for a long time, it was understood in physics that light is a form of energy, and therefore it can be used to extract electrons from a conducting surface and generate electricity. Okay. And by studying the properties of such an experiment, we could understand more about optics. Okay. And of course, by the time photoelectric effect was established experimentally, uh, light was well understood as a wave phenomena, because all the wave optics experiments like YDSC etc. had been established. So the study of photoelectric effect is with the background that light is understood as a wave phenomena by then, electromagnetic wave phenomena. So keeping that in mind, so definition of photoelectric effect is basically the generation of electricity, or you can say electric current, by the incidence of light. By light we mean visible light. Okay, this is called photoelectric effect, and this is basically created by the generation of electrons, free electrons, but they're given a specific term, photoelectrons. Okay, so it is created by the generation of photoelectrons, that is free electrons. Okay, you can say, which are brought to the surface of a metallic body. Okay, free from its lattice by the incidence of light on a metallic body. Okay, so that is another way of understanding what photoelectric effect is all about. That you generate photoelectrons, that is free electrons, which are completely free from the lattice of the metallic body on its surface by just making light incident on the metallic body. Okay. And another background to understanding this thought process is that by the time photoelectric effect was being explored, thermionic emission was already understood. Thermionic emission, as you might have read in 9th, is the generation of electric current via heat. Okay, so instead of making light incident on a metallic surface, if you heat a metallic surface, apparently free electrons can emerge onto its surface, and those free electrons can be used to generate and demonstrate an electric current. So thermionic emission was already an established effect. So it was thought that, okay, if direct heating of the metallic surface can bring free electrons outside its lattice onto the surface, then light being a form of energy, suitable interaction between light and the free electrons within the metal can also create the effect of bringing the free electrons outside the lattice. So that is another part of the thought process. So anyway, so the experimental setup was something like this. So to establish that photoelectric effect is taking place and to measure its various properties, what we do is we define a system like this. or we set up an experimental apparatus like this, that we have two metallic plates, the so-called cathode and anode. Okay. Now these metallic plates are placed inside a vacuumized vessel, vacuumized so that you make sure that there is no ionized gas, or there are no gas ions possible which might be conducting electricity. So just to make sure, so it is not like the container has gas at low pressure or anything. It just does not have anything. It is vacuumized. Okay. And then of course you connect the cathode and anode across a voltage such that the anode is at a positive voltage compared to the anode. I mean compared to the cathode. So this is conducting wire, and of course you would also have a sensitive ammeter, something more like a galvanometer, which can measure current in microamperes. Okay, so now the idea is, see, because this is vacuumized, okay, you are not going to experience any electric current in the galvanometer, or if you place an ammeter, okay, because there is a break in the path of electricity. There is no conducting path between the cathode and anode. Okay, but the moment we make light incident on the cathode under the right conditions, if there is photoelectric emission, then we will register a current. Because if there is photoelectric emission, then the electrons will get free of the lattice of the metal plate or the cathode and come onto the surface. And under the action of the voltage across, okay, they will get accelerated towards the anode. And as they get accelerated, then they will conduct through, and we will a current will be established. Okay, so that is the whole point. So if visible light under suitable conditions that it produces photoelectric effect is incident on the cathode, then we will be able to measure a current in the galvanometer. So when visible light incident on the cathode generates photoelectrons, okay, then an electric current, okay, is established. Okay. So this electric current is also termed the photocurrent in the circuit, because it is generated by photoelectric effect. Okay, so yes, this experiment conducted under the right circumstances, and what they are we will discuss. it does happen this way. We are able to establish a current even though there's vacuumized tube and no matter typically between the cathode and the anode. Okay, so it does demonstrate the phenomena of photoelectric effect. Okay, but now let's understand what are the circumstances and what are the properties, of the electric current that is established. So one thing which is very interesting. So keep in mind that let's say you're going into the experiment thinking that light has the wave property which we have just studied, using interference and diffraction experiment. So we understand that is some kind of a wave phenomena. So if photoelectrons are getting emitted, there is a process of energy transfer between the electromagnetic waves and the lattice structure. Okay, and that energy transfer is resulting in the electrons coming outside the conduction band, because even in the conduction band they have some kind of negative energy. They have some kind of stability within the lattice structure. So that stability for the conduction band electrons or for the valence electrons is such that the electrons can move about within the lattice, but they can't really come outside the lattice because they do have some negative energy, so they have some stability. But by the transfer of energy from the light beam onto the lattice, what is happening is some of those conduction electrons, or the electrons which are in the conduction band, so called, they are valence electrons, they are completely free from the lattice. They are able to gain that energy and come outside onto the surface, uh, completely free of the lattice. So such electrons are then called the photoelectrons. Okay, so that is the background. Okay, so what we observe now in the experiment is something very interesting. Okay, we observe that if the experiment is conducted using monochromatic light of wavelength, let's say lambda, and intensity I, okay, then very important property. What happens is that if different wavelengths are tested at a given intensity and a given voltage, that is the voltage across the cathode and anode. Okay. Okay. What we observe is that photoelectric effect or photocurrent appears only for wavelengths which are which are greater than a certain threshold wavelength. Okay. So that means photoelectric effect takes place for wavelengths less than a threshold value. Okay. Sorry, this inequality is less than. So only if the wavelength of light, the monochromatic light, is less than a certain threshold, okay, then this happens. And the other thing that is observed, the value of the threshold wavelength, okay, is independent of intensity of light and voltage across the cathode and anode. Okay, but depends on the metal used for the cathode. Okay. So that means basically what is happening, the threshold, it is a property of whichever metal the cathode is made of. Okay, so now if you think about it, this kind of contradicts the wave nature of light, because whether or not electrons are getting generated should depend on a certain threshold of energy. If the threshold of energy transfer between the wave, the light wave, okay, the light beam and the metal is greater than a certain lower limit, then there should be enough energy to bring the bring the valence electrons out as photoelectrons. So naturally, if it's not happening for a certain situation, then increasing the intensity of light should do the job, because increasing the intensity of light means the incident energy is getting increased. So there should be greater probability of energy transfer and the valence electrons getting free from the lattice. But apparently that doesn't happen, because if we choose a wavelength which is less than the threshold wavelength for that particular metal, then it doesn't matter how much intensity of light is incident. We can double it, we can triple it, but nothing will happen. Okay. So that means somehow the question of whether or not enough energy is available for valence electron to come out, that depends on the wavelength of light. Okay. Whereas the wave nature of light does not say anything like that, that the amount of energy incident from a beam should depend on the wavelength. It should only depend on the intensity. Okay. So this basically contradicts the wave nature of light. So the explanation for this was given by photon theory of light. Okay. So this experimental result, you can see it cannot be explained by the properties of light as a wave, as an electromagnetic wave. So the proper explanation for it is therefore given by, one of the landmark theories proposed, okay, was the photon theory of light established by Einstein. Okay. So, so this photon theory gave an explanation for photoelectric effect. Okay. So we will not get into the thought process behind the photon theory of light. Okay. But I'll just give you a hint by saying that by then a lot of phenomena like spectral emission of light from atoms, etc., were already known, okay, as experimental facts. The spectral emission concept, that when light is emitted from atoms, then the value of the wavelength of light is such that the angular wave number 1 by lambda is always in a sort of series where it is proportional to 1 by n square minus 1 by m square, where n and m are integer values or natural number values. Okay. So things like this, the Lyman-Balmer series, etc., they were experimentally understood, but there was no proper theory that explained why that happens, why we cannot have continuous emission, spectral emission, and why we have what is called the line spectrum in the emission of electromagnetic waves from atoms. Okay, so things like that were already established in physics. So photon theory of light, it sort of came from the introspection of all these things, not just the photoelectric effect experiment, but also the behavior of the spectral emission in forms of line spectrum from atoms. okay, or from various elements, okay, and that every element had its own signature set of lines. You must have studied in chemistry the Lyman series, the Balmer series. They had signature values for particular elements. Okay. So that was also part of the establishment of the photon theory. So we will just understand the elements of photon theory. Okay. So, so the important elements is first of all that the energy propagated through a light beam, so called, is quantized with a photon being a single quantum, you can say like a single packet of energy, capital E, where E is hc by lambda. Okay, and h is of course Planck's constant. Okay, so note down this point. This is the first important point for us here. Energy of photon is given by this formula. Okay. And what is a photon? Basically, it is a single quantum or single packet of light energy. Okay. Planck's constant, as you know, has an approximate value of 6.63 into 10 raised by minus 34. Yeah, it is h mu. Okay, because you know that, so c by lambda is the same thing as Okay, now second thing is that photons are what we call massless. That is, they have zero rest mass, and therefore are not particles in the classical sense, but are packets of quanta of energy. Yeah, rest mass is the mass of a particle when it is at rest. In relativistic physics, there is a difference between dynamic mass and rest mass. So, mass of a particle increases with speed or momentum, hence the term rest mass. So, the way we know it in classical physics, what we studied the last 2 years, it is nothing but rest mass only. But when subatomic level particles are accelerated to very high speeds, such that their speed is approaching the speed of light, then the phenomena of dynamic mass comes into play. Okay. Photons have linear momentum. Okay, and there are experiments to prove this point that they have linear momentum, though they do not possess rest mass. No, the question of dynamic mass also does not arise, Ganesh. Okay, because dynamic mass is a function of rest mass and speed. So basically, we should just not visualize photons like particles which are moving at the speed of light. We should not think of it like that. You just think of it like a packet of energy. So I said they're not particles in the classical sense. So that is why you can see that the relationship of linear momentum is also different. It has nothing to do with mass. It is energy divided by speed of light. So this is all a little strange initially, because there is also the gap that we don't understand relativistic physics at this level as a separate topic. So you have to just understand these things as postulates. Okay. These important elements of photon theory of light, these are basically like postulates. They are not derived from anything else. They are just postulates. Yeah, de Broglie, but de Broglie applies to matter waves, not photons. So yes, you can say that this equation, when it is inverted and applied to a moving particle which has linear momentum mass into velocity, then that gives us the de Broglie wavelength. But here we are talking about photon theory, so it's a little bit away from de Broglie concept. And of course, this photon theory of light was established before de Broglie's hypothesis. So that's another important thing. Okay, I mean, de Broglie hypothesis came from a lot of considerations, not just this single equation which comes from photon theory. So, the common joke that de Broglie got the wavelength for just inverting the equation p is equal to h by lambda, that lambda is equal to h by p, that is in fact incorrect. Okay, there is a lot of experimental consideration that matter also creates waves. Like an electron in an orbital motion, or an electron stuck between two potentials moving in linear motion or whatever within a lattice, that that motion of the electron also has a wave nature to it, and therefore has a certain wavelength, and then that wavelength is given by that formula, de Broglie formula. So there is a lot of theory and experiment going behind that also. But that is a question of matter waves. So those are classical particles which have a wave nature to their motion. Okay. This is photon theory of light, so very far away from classical particles. Okay. Now, the very important concept here about interaction of light and matter. Okay. For example, emission of light from atoms. So what happens in the process is that electrons transition from higher energy to lower energy orbits and emit photons. The process. That's an example of interaction of light and matter. Or another example could be the absorption of light by matter. That is, electrons in lower energy state or orbit can absorb light and transition to higher energy state. So that's another example of interaction of light and matter. Or for example, photoelectric effect. Metallic body absorbs light, and in the process valence electrons, okay, which we can also call conducting electrons, come out of its lattice onto the surface with some momentum even. Sometimes they come out with momentum, as free electrons, which we call the photoelectrons. So these are all different examples of interaction between light and matter. Now this is just the examples of interaction. Now I'll tell you how photon theory, what it says about these interactions, but note this down first. Yeah, I mean, I'll explain that, why that happens, Ganesh. So in all these interactions, so any such interaction, okay, a single event involves a single photon only. So this is the important thing to understand. So let's understand that in context of the examples that we talked about. So let us say these are the energy levels inside an atom. Very soon we'll study about them, Bohr's model of atom. So ground state, first excited state. Now suppose we are talking about the first thing, that an electron makes a transition from a higher energy state to a low energy state. So in the process it will emit light. So that will be a single photon, and that single photon will have an energy of, in this case, E2 minus E0. So for example, an electron relaxing from second excited state to ground state, it will, so that single electron undergoing the transition is a single event, so it will emit a single photon of that energy, which is equal to this. Okay, or the reverse of this. Suppose we want an electron, let's say we want an electron in the first excited state, we want it to transition to the second excited state. We want to excite it to the second excited state. So it must be incident with a single photon which has the required energy. If it is incident with two photons simultaneously which have energy half of the required transition energy, that transition will never happen. For the transition to happen, a single photon of energy, exactly the amount which is required for the transition, should be incident on it. So an excitation of an electron will result from absorption of a single photon. Okay, and this becomes the reason why we have that signature line spectrum for the emission of EM waves from various different elements. Each element has its own signature set of wavelengths, which are the lines on its spectral emission. So this is just the quantum nature of atomic physics, okay, and light. Yeah, that is the quantum nature, because see what happens, Ganesh, that within the structure of the atom, electrons can only exist in certain allowed energy levels. So if you give it more energy than, for example, E2 minus E1 here, it cannot absorb that energy because it cannot exist at an energy which is larger than E2 but less than E3. You understanding the point? The energy levels in between the allowed lines, okay, or the allowed values, okay, or the allowed what we call quantized energy states. So in between those states, the energy states are not allowed. Okay? They are forbidden energies. They can only exist at certain specific values of energy. So that is where quantum mechanics is strange compared to classical physics. It's a little bit difficult to accept initially because we don't see that kind of phenomena in our everyday experience, or at the experimental level in classical physics is standing waves and resonance. That a given string can vibrate only in certain allowed values of frequency, or certain quantized, or certain members of a harmonic series. It cannot vibrate in a continuous spectrum of frequencies. So that is another system which is naturally quantized. But atomic systems, photoelectric effect based systems, they all exhibit the quantum nature of light and matter. So it cannot happen that you're given 1.2 times the amount of energy through the photon, but the electron has accepted only that much energy and made the transition. Okay. Either it has to have the exact amount of energy for that transition, or otherwise the electron will simply not absorb the photon. It will reflect back the photon. Similarly, when the electron relaxes from higher state to lower state, it cannot give off the energy in as the sum of two or three different packets of energy. It has to be a single packet of energy emitted, which is coming from the single transition. Okay. So you can say that this was all part of experimental evidence from atomic physics, and then gradually the theory of quantum mechanics moved forward, and photon theory of light also part of that quantum mechanics establishment moved forward, and the explanation for all of this came from that. So now let us understand the role of this concept in photoelectric effect. Okay, so what happens is that any given metal has a material property called work function phi. So this work function is the energy, that is minimum energy, okay, needed by a valence electron to come outside the lattice onto its surface as a free electron or photoelectron in case of photoelectric emission. In case of thermionic emission, these electrons are then called thermions. So that work function is an inherent property of the given metal. So different metals have different values of work function. So therefore, okay, if light, let's say monochromatic, of lambda and intensity I is incident on a metal surface, then a single electron valence electron can absorb energy from a single photon only. Okay. So therefore, condition for photoelectron generation is that the energy of the photon must be greater than the work function. Okay. And that is independent of intensity. Or lambda should be less than hc by phi. Hc by phi becomes what we call the threshold wavelength. Okay. So this is the success of photon theory of light in explaining the experimental phenomena of threshold wavelength. Okay. So now let's come back to the photoelectric effect experiment. Now let's understand some of the other properties. So for monochromatic light, wavelength less than threshold wavelength and intensity I. If we measure the photo current versus the voltage that we've applied, and we observe something very interesting, that even at zero voltage there is some current, but as the voltage increases, the current increases and then saturates. So for this kind of thing, the observation is that the photocurrent is non-zero even for voltage applied being zero. Okay. So this is the evidence that a certain percentage of photoelectrons come onto the surface with non-zero momentum, and migrate to the anode due to their momentum. So that is the evidence that there is non-zero current even when the voltage is zero. Secondly, current increases with increase in voltage, okay, up to a saturation value. Now, further experiment shows us that the saturation current depends on the intensity of light and the area of the cathode plate exposed to light. So, in other words, the saturation current basically depends on what we call photon flux. onto the cathode. By photon flux, we mean the number of photons incident per unit time. Depends on this factor only. Okay. So make a note of this and we'll discuss. Work function is the property of the metal, Ganesh. It has nothing to do with the light. Work function has to do with how strongly the valence electrons are still established within the lattice. How much stability energy, negative energy they have within the lattice. Valence electrons are not bound to the atoms individually, but they are bound to the lattice still. To bring them outside the lattice, we need to supply a minimum amount of energy. So that energy depends on the lattice structure. No? It's not anything to do with whether or not light is incident, because we can make those electrons come out even by heat, thermionic emission. So that is nothing to do with the incident light. No, there's no way to calculate the work function. It is an experimentally established quantity. So photoelectric effect experiment is, for example, one way of understanding how much the work function is. Because there's a relation between threshold wavelength, which you can measure, because you can make light incident at various different wavelengths and see that for which wavelengths we are getting photocurrent, which ones we are not getting photocurrent. Okay. So the wavelength from which the photoelectric emission starts, that becomes the threshold wavelength. Okay, so very soon we'll do a couple of numerical questions and these things will become more clear. But now another interesting thing is that if we apply a reverse potential, that is the potential of such that the anode is given negative potential compared to the cathode, then we see that the current stops at a certain value of reverse potential. That is called the stopping potential. So the next thing, if the polarity of voltage is reversed, that is voltage given to anode becomes less than the voltage given to cathode, or V of the anode minus V of the cathode is negative, okay, then photocurrent I drops sharply with negative voltage such that I becomes zero at a certain value of reverse voltage called the stopping potential. Okay. Now, interestingly, the stopping potential is not affected. It is not affected by intensity of light. Okay. It only depends on two things: the wavelength and the work function of the cathode. Okay. So in other words, if we were to, for example, carry out using light at two different intensities. Okay. So we would see this kind of thing. If this is intensity I1 at wavelength lambda, then we repeat the experiment but at a higher intensity of light, keeping everything else the same. So the same wavelength but intensity I2. Okay. And both of these are for the same cathode, that is the same metal, the cathode. I2 is greater than I1, but lambda is same for both. So we'll see that stopping potential remains the same, but the saturation current increases because the intensity has increased. So the photon flux is increased. Okay, so hope this point is clear here. Now, the value of stopping potential actually can exactly be calculated on the basis of the work function and the incident wavelength. Okay, so calculation of stopping potential from the work function and incident wavelength. So the idea is that when the negative voltage is equal to that stopping potential, what happens is that the um, the photoelectrons coming out onto the cathode surface are decelerated by the electric field between the cathode and anode. When a negative potential is applied, instead of being accelerated, they are getting decelerated. Okay, so if the negative potential equals the stopping potential, okay, then even the fastest of photoelectrons are decelerated enough to not reach the anode. That is the concept, and the photocurrent becomes zero. Okay. So the condition for that is that this the maximum kinetic energy of a photoelectron is given by hc by lambda minus phi. Okay. This is of course, for this to happen, lambda has to be less than threshold wavelength. So if the photon is giving the electron an energy of hc by lambda when the electron gets absorbed, but out of that phi amount of energy, the work function amount of energy is the minimum energy required for it to come out onto the surface. Okay. So only a very small percentage of the electrons will miraculously come out of the surface with all the energy intact, without losing any energy because of collisions and thermal effects and things like that. But there is a small percentage of the electrons which can come out with the maximum possible energy, which is maximum possible kinetic energy, which is hc by lambda minus phi. Now, if these most energetic electrons are also getting decelerated enough, then the work done by the electric field, EVS, should be enough to cut that kinetic energy altogether. So the maximum kinetic energy becoming equal to E into stopping potential, or the work done by the reverse electric field. That becomes a condition for zero current. Okay. So condition for the photocurrent to be zero is this. So from this we can see that hc by lambda minus phi is equal to EVS. So the stopping potential is given by this simple formula. So this is how it depends on these two factors, the wavelength of the light and the work function, and it is independent of intensity of light. It is independent of all these things. The intensity, the plate area of the cathode doesn't depend on all that. It only depends on per packet of energy, how much energy is coming, hc by lambda, and how much of that energy is required for the electron to come out, which is phi. It depends on the difference of these two things. No, no, lattice energy is different thing. Uday, don't confuse it with work function. You just understand work function as the definition given. That is the minimum energy required for a conduction electron to come out onto the surface as a photoelectron. That too for a metal. Okay. Lattice energy is a more general term. Okay. In chemistry. Okay. This is specifically for the purpose of metals. I mean, that is pretty evident from the experiment. Na? The more the voltage, negative voltage we apply, the lesser the current will become. Because electrons coming out onto the surface are coming with a range of kinetic energies. Na? It's not that all of them are coming with maximum kinetic energy. So some of them are having less kinetic energy. So the more the voltage we apply in the reverse direction, the more the percentage of electrons coming out do not reach the anode. Now the moment that voltage hits the stopping value, the stopping potential, that percentage of electrons not reaching the anode becomes 100%. So the current becomes zero. Okay. All right, so we'll take a break here and we will discuss a couple of numerical type of problems based on photoelectric effect immediately after the break. And then we will discuss the basic elements of Bohr's model of atom, which anyway you are quite familiar from in chemistry, but in context of what you require for solving physics problems, we'll discuss a little bit about it. Okay, so let's just take a break for 5 to 10 minutes and continue then again. Okay, people, let's continue ahead now. Yeah, so now let's look at type of numerical calculation, and in one question we will understand all the various aspects of calculation that we can do. Now before we start the calculation, just a thing about the units used in modern physics typically. Energy, we use a unit called electron volt. Okay. So 1 electron volt is basically the work done on an electron, okay, or charge equal to, plus minus of electron. So whether it is electron or proton going through a potential difference of 1 volt. So 1 electron volt of energy is literally equal to 1.6 into 10 raised power minus 19 coulombs into 1 volt. So it is equal to the same thing as electronic charge in joules. So the preferred unit that we use for energy in modern physics is electron volts. And the other thing is that in the calculation hc by lambda, the quantity hc is, okay, joule second. Okay. So that can also be shown to be approximately 1242 electron volt nanometers. Okay. Here, this unit, when you convert, this will become, it will be in joule meters. Okay. So this has to be multiplied by a factor of 10 raised power minus 9. I mean 10 raised power 9 divided by 1.6 into 10 raised power minus 19. When you do that, it comes out to be this. So for example, we want to calculate the energy of a photon of wavelength, let's say 500 nanometers. So one very easy way of doing that calculation is that it is 1242 divided by 500. Now that will be in electron volts. That will be, so this unit, electron volt nanometers. Okay, so let's look at a typical question now. So monochromatic light of wavelength, which is 600 nanometers, at an intensity of, let's say, 2 watt per meter square, is incident on the cathode of surface area, say 20 centimeter square of a photoelectric experiment, made of a metal of work function phi equal to, let's say, 1.6 electron volts. So from this we want to calculate the saturation current. Okay. Now also one additional thing that will be given to you in questions like this is that the probability factor of photoelectric emission. Now that is, let's say, 10 raised by minus 2. So what does this probability factor mean? It means that if an electron is incident with a photon, the probability of an incident photon generating a photoelectron was just because the energy of the photon is greater than the work function doesn't guarantee that every photon incident will emit a photoelectron. There are other factors also. There is thermal energy, there is, the angle at which the collision happens, this, that. So, and there is quantum mechanics. So end of the day there is probabilities, other probabilistic factors. So only a very small percentage of actual photons incident end up in resulting in a photoelectron getting emitted. So that probability factor is usually of the order of 10 raised by minus 2 or minus 3 or even smaller. Okay, so here the probability of an incident photon generating a photoelectron, that is 1 upon 100 or 10 raised by minus 2. Yeah, so we have to calculate the saturation current, we have to calculate the maximum possible kinetic energy of an emitted photoelectron, and we have to calculate the stopping potential. Yes, very good. That's correct, Ganesh. Okay. So here for the purpose of this one, let us take Hc equal to, again, usually this is given in a JE paper, the value you have to take. And sometimes it might be an approximate value also, like 1200 instead of. Yes, that's correct, Ganesh. Okay, so let's start with this question. So first of all, on the cathode of a certain area, you have light of certain wavelength and energy incident. Sorry, intensity incident. So from that we can calculate something called photon flux. That is number of photons incident on the cathode per unit time. Okay, so how do we calculate that? So intensity is energy incident per unit time. So intensity into per unit time per unit area. So intensity into area will become energy incident per unit time. Divide that by the energy of the photon, that becomes the number of photons. Okay. So intensity is energy incident per unit time per unit area. So intensity into area is total energy per unit time. So divide that by E. So this becomes the photon flux. So in this case, the photon flux it was 2 watts per meter square, okay, into the area of 20 centimeters square. So that is 20 into 10 raised power minus 4 meters square, divided by the energy of the photon. Now the energy of the photon, hc by lambda, you can write as 1242 divided by 600. So that is becoming electron volts. So we can also write that as 2.07 into 1.6 into 10 raised power minus 19 joules. So here, so you can see the units. Watts per joule will give you per second. So this is 4 upon 2.07 into 10 raised power minus 3. Now I'll keep this separate because it will cancel out. Okay, so I'm not incorporating this into the calculation. So this is per second. That is a photon flux. So just make a note of this part, then we'll discuss ahead. So now this is the number of photons incident per unit time. So from that we'll get the number of photoelectrons emitted per unit time by multiplying by the probability factor. Okay, so now the next thing here is the photoelectron flux. That will be equal to the photon flux multiplied by the probability factor. So photon flux is the number of photons incident on the cathode per unit time, and this is the number of photoelectrons emitted per unit time. Yeah, Ganesh. Okay. So now you will see that basically saturation current, it is the value of current when 100% of emitted photoelectrons are conducted in the circuit. Okay. That is, none of the photoelectrons emitted get pushed back to the cathode. All of them reach the anode. So the saturation current will be nothing but the photoelectron flux multiplied by electronic charge, because there's number of electrons per second, so multiply that with charge per electron. So this factor here becomes into the probability factor, or you can just understand this as photon flux. Let's say we call it Ne. This is, I mean, photoelectron flux, so that will become intensity upon into area upon hc by lambda multiplied by the probability factor, this kind of thing. So now this becomes into electronic charge. So in our particular case here, it becomes, so this was per second and this was coulombs. So the whole thing becomes amperes. So you can see it is a little less than 20 microamperes. Maybe 19 point something microamperes. And these are the typical kind of values also in a photoelectric effect experiment. In fact, the probability factor might be a little bit less than what I'm saying. It might be more of the order of per thousand rather than per hundred. So it's a very logical type of calculation, and all calculations in modern physics are that way only. Just the basic things, if you remember. Okay. Now the rest of the things are very simple in this. You want to find out the maximum kinetic energy, that is just the energy of the photon minus the work function. So hc by lambda minus pi. So now the stopping potential, so one thing you can keep in mind is that whatever is the maximum kinetic energy in electron volts, same becomes the value of the stopping potential in volts. If you just remember the definition of electron volts, that will become clear why that happens. So you don't need to separately calculate. And one more thing you can calculate here is the threshold wavelength. The threshold wavelength for the cathode's metal. Okay, so Hc by lambda threshold is nothing but the work function. So whatever this is, this will come in nanometers. It's probably going outside the visible spectrum of light also. That means any sort of visible light over here will create photoelectric effect. Okay, so if you just revise through this question, you will see all the types of calculations required in any photoelectric effect question that is contained in this question itself. Any other objective question or any other um, you know integer answer type question, numerical type question will be a subset of these kind of calculations. Nothing more than this is going to be there in photoelectric effect. Yes, photoelectric effect is completed. But then the concept of photon theory of light and these type of calculations also become important in questions where there is atomic physics involved. So photoelectric effect itself is completed, but the photon theory of light will be carried forward in the next chapter also, which is the Bohr's model of atom. So we'll look into the fundamentals of Bohr's model of atom. It's a very simple chapter. Again, very simple type of numerical problems also. As long as you know how to handle the maths, what type of unit systems and all that. So Bohr's model of atom, it comes with certain assumptions. So the assumptions are that basically carried forward from Rutherford model, that all the positive charge is contained within the nucleus and most the mass is contained within the nucleus. So the electrons move in circular orbit around the nucleus. So the first thing is that all positive charge, okay, and most of the mass is contained in the nucleus, okay, and also the size of nucleus is a very small fraction of the size of atom. I mean, this is just a factual thing. It's not so much Bohr's model. You know that radius of nucleus is of the order of Fermi's, or 10 raised by minus 15 meters, whereas the radius of atoms is of the order of Armstrong. or 10 raised power minus 10 meters. So as far as volume is concerned, you can see it's not comparable only. And this is the volume of the nucleus will be of the order of 10 raised power minus 15 times the volume of atom, because the radius size is 10 raised power 5. So volume is radius cube. So it's a very, very small fraction of the volume is actually occupied by the mass of the atom. The mass of the atom is completely concentrated to a super dense structure called the nucleus. And the electrons, which hardly have any mass compared to the mass of the nucleus, they are literally orbiting in empty space, which is most of the volume of the nucleus. So anyway, coming back to the assumptions, the second assumption is that electrons orbit in circular path around the nucleus. In fact, you can actually treat the nucleus like a point mass compared to the atom. Okay? So mv square by r will be equal to, okay. So part of this assumption here is that electrostatic attraction is the centripetal force, or provides the centripetal acceleration. Or if you want to go into that fancy circular, I mean the non-inertial circular frame of the electron itself. So in the electron's frame, the centrifugal force will be balanced by the electrostatic attraction. But we can just visualize as if we are in ground frame. Now the third thing is where it departs from the previous model or Rutherford's model. That is the orbital motion of electrons. Okay. Angular momentum is quantized. MVR is equal to NH by 2 pi, where N is the principal quantum number of a particular orbit. So N is equal to 1 for ground state, first excited state. And so on and so forth. Okay. So N equal to N is the N minus 1th excited states quantum number. And H is of course Planck constant. So I mean here you understand all these things. M is mass of electron. So approximately 9.1 into 10 raised power minus 31 kilograms. E is charge of the electrons. H is Planck's constant. Now, where this comes from is a little bit complicated. So, this basically comes from very deep statistical analysis that was done of the line spectrum. Now, line spectrum of emission from atoms. Okay, that showed that 1 by lambda was proportional to 1 by n square minus 1 by m square, where n and m were the principal quantum numbers of the excited of energy levels. Okay, or simple terms, what we call orbits. So now when we understood that, okay, 1 by lambda is proportional to energy, or because energy of the photon is hc by lambda. So we saw that the energy difference was proportional to 1 by n square minus 1 by m square. And then the energy of the orbit has something to do with angular momentum, because it is half mv square minus ze square upon 4 pi epsilon naught r. So it turned out that the energy is inversely proportional to 1 by r, the magnitude of the energy. Okay. And angular momentum is equal to mvr. So from this it was established that, so backward calculation, lot of statistical analysis and all that. So from that it was established that the angular momentum is equal to nh by 2 pi. I mean, not just statistical analysis, but the actual recording of data experimentally. So the different members of the line spectrum series that you get, intensity of light versus wavelength. So your line spectrum looks like this. You have a cluster called the Lyman series. Then you have a cluster called the Balmer series. So the values of these different wavelengths against the atomic numbers of the various elements they came from. So that is the whole science of spectroscopy. You might have heard that spectroscopy in itself is a branch of physics, and it involves literally like thousands of laboratories around the world recording the data from these experiments, then scientists doing the statistical analysis on that data, and then developing the mathematical model to back calculate what information those spectral emissions are giving us. And it is part of that huge exercise that it was finally established the value of h, the Planck's constant, the relation between angular momentum and this quantum number. Okay. So that is something we will not get into at our level. We'll just treat it like a postulate. This is like, again, it is one of the postulates of Bohr's model. But there is a lot of experimental data and then statistical analysis on experimental data that goes into the postulate. It's not something that came in somebody's dream overnight or something like that. And then the final thing about the assumptions of Bohr's model or postulates of Bohr's model is that the total energy of an electron in orbital motion, obviously, is the sum of its kinetic energy and its interaction energy electrostatically with the nucleus. So when we put together these three mathematical equations that are part of the assumptions, you will see we get the whole result of Bohr's model. That is the formula for the different energy levels, and therefore the formula for energy of photons emitted or absorbed during transitions. And because the values that we get from those calculations agree very well with experimental data, but from specific type of atoms, that is hydrogen like atoms. So that is why Bohr's model of atom is considered highly successful for hydrogen like atoms where the nucleus is small. So Z, the mass number, is not more than about 6, 1 2 3 4 5 6, that kind of thing. Whereas Z, the atomic number, not the mass number, is up to about 6, and where typically we have one electron in orbit. So a Bohr-like atom or a hydrogen-like atom would be like a hydrogen atom or a deuterium atom or a tritium atom, or for example a singly ionized helium atom. So the physics of all these kind of structures where the nucleus is not consisting of very large number of protons, okay, up to about 6, not more than that, and a single electron is in orbit around the nucleus. So the physics of these kind of atoms or ions is almost 100% correlated with Bohr's model. Whereas the moment we are looking at more complex sort of atoms where the mass number is more, and also we have larger number of electrons in orbit with various different shells, then the actual experimental data starts to move away from what Bohr's model predicts. And that is where the more complex models like Sommerfeld's model of atom, and of course modern day theory is the this thing, the cloud structure quantum mechanics model of atom. It's quite far from this classical model. Those kind of things take prominence. But for hydrogen and hydrogen-like atoms, to this day, Bohr's model is 100% accurate, near to 100% accurate. Okay. So anyway, let's put together the assumptions. So we have mv square by r is equal to ze square upon 4 pi epsilon naught r square. So from this, we have this relation that v square is equal to ze square upon 4 pi epsilon naught mr. That is, let's say, our equation 1. Then we have mvr is equal to nh by 2 pi. So again from this we have v is equal to nh upon 2 pi mr. And we have so if we put this thing over here, so we can see that or that the energy is half the potential energy or negative of the kinetic energy. Okay. This is true about circular orbit in case of gravitation also, because central force proportional to 1 by r square. Now from these two we can see that nh by 2 pi mr square is equal to ze square upon 4 pi epsilon naught mr. So n square h square upon 4 pi square m square r square is equal to ze square. So from this we see that only certain radii are allowed according to the values of n. So the allowed values of radius become n square h square upon pi m. Okay. So the radius of the orbit depends on the state of the quantum state, principal quantum number, and the atomic number into a standard constant, where that standard constant is this. It works out to be 0.693 angstroms. Okay. And now you put that back in the formula of the energy. Somewhere I missed an e square, no? Because this term should be e to the power 4. So wait a minute. Somewhere I missed an e square. In the radius formula, I missed the e square. Let's see. So r is equal to, yeah, 0.53 Armstrong. Sorry, my mistake. So this value is approximately 0.53 or 529, not 0.69. So this formula here, it becomes n square by z times 0.53 approximately Armstrongs. Okay, so now here also, as you can see, this energy is okay, because this is the ground state energy, okay, for hydrogen atom z equal to 1. That becomes minus of this term. So this is a universal constant. So the energy of the nth quantum number, okay, so this is the energy of electron in n minus 1th excited state of an atom of z equal to z. That is given by this formula. Ganesh, we just substituted this over here, but R I think has another e square which I forgot here. Okay, so this gives us a picture of the energy levels. So what this tells us that in an atom, electrons exist in orbital states of certain allowed values, or what is called quantized states, where the energy of the state is given by, and the radius is given by, so for example, for hydrogen atom, the ground state is n equal to 1. So the ground state energy is minus 13.6 electron volt. The first excited state is n equal to 2. So that is minus 13.6 upon 4. Okay. Then the second excited state, like this. So as you go further up, the difference of energy levels becomes lesser and lesser. But for example, if you look at helium, so helium plus ion, okay, the ground state energy will be minus 13.6 into 4, because Z is equal to 2. The first excited state will become, The first excited state of helium is equivalent to the ground state of hydrogen. Okay. So now the thing is that if an electron in some excited state is to make a transition to a higher energy state, in the process it must absorb a photon. So hc by lambda must be equal to yeah. So where this is the energy of m minus 1th excited state. This is the higher state. This is the lower energy state. And this. So that's all there is actually to Bohr's model of atom. Now, one important thing to remember about Bohr's model of atom is that spectral emission, that if an atom is at an excited state, basically not an atom, if we can say a set of atoms, or basically a sample of an element is at an excited state, nth excited state. For example, E1 is the first excited state, that is quantum number is 2. E3 is the third excited state, quantum number is 4. Okay, then atoms in this sample will tend to relax to lower states, and in the process n plus 1 C2 different wavelengths will be emitted. This is combinatorics. N plus C2 is like that. Okay. So just let's understand with an example. So for example, a helium plus sample at the third excited state. Okay. That means it's existing here. So the principal quantum number is 4. Okay. So if it's in the third excited state, the number of wavelengths emitted in its spectrum, that will be 4C2. So that is 6. So let's understand how that is happening, because there could be a direct transition, so that is giving us one wavelength. There could be a transition like this, and then eventually this, so that is giving you two other wavelengths possible. There could be a transition like this, so that's another one possible. Then from this it could give you this. Okay. And back here, so that's by lambda 3, and also here. So there are 6 different wavelengths. So hc by lambda 1, for example, would be E3 minus E0. This would be the shortest of the 6 lines in the spectrum. The shortest wavelength, that is. Okay. Whereas hc by lambda 4 in my diagram is E3 minus E2. This is the longest wavelength. Okay. So this is an important concept to remember, that when you are at the nth excited state, so your principal quantum number is n plus 1. How many different transitions are possible from that? So that is n plus 1 C2. So for example, from the third excited state, there are 4 C2 number of transitions possible. So there are 6 transitions possible to a lower excited state. So samples of atoms in the third excited state will emit 6 distinct wavelengths of light. So from a sample of atoms, if I'm getting 6 wavelengths, I know that it is in the third excited state. If I'm getting 3 wavelengths, I know it is in the second excited state. If I'm getting 10 wavelengths, then I know that it's in the fifth excited state. I mean, yeah, fourth excited state, but n equal to 5. Okay, so this is an important little tip for solving problems. Okay, so now with this information that you've learned today, if you just go through the solved examples in H.C. Verma from Bohr's model of atom and Bohr's and photoelectric effect chapter, you will understand the various different types of questions that are asked at JEE level. And then you can just do previous year paper questions, and that should be enough for this. It's not really a difficult topic, but at the same time, it should be 100% scoring topic for you, because it's so easy. And also the questions are generally not time taking, so you should look to score from this. Okay. So that's it for today's session, people. Next session, we will discuss some questions of Bohr's model of atom, but then we will also discuss about this thing, nuclear physics and X-rays.